All right, hello and welcome. So today in this short lecture, we are going to be doing something which is called the Riemann's method. Okay, so so we know that you have a second order PDE, and we've seen this before. If you have some LU is equal to g of xy, this is hyperbolic. So this is hyperbolic. If, as you remember, if there's b squared greater than 4ac, and it has two families of real characteristic curves in the xy plane. The equations of this are given by xi is equal to f1x xy. So that's some c1, and eta equal to f2 xy is equal to some c2. And we have also seen that a second order PDE in two variables, if we have this which is hyperbolic, then this can always be reduced to this form which we call the canonical form, and this is some f of x y u x u y. Now suppose let us have let's take L of u is equal to del 2u del x del y plus a of del u del x plus b of del u del y plus c of u is equal to some f of xy. Okay, and let v of xy be an arbitrary function that has continuous second order partial derivatives, and we will call L star of v as del squared v del x del y minus a, sorry, not a, but del x of av minus del y of bv plus cv. And we're going to introduce the following. We're going to introduce m is equal to a uv minus u del u, sorry, del v del y, and n as b uv plus v del u del x. Okay, so then you can see that vlu plus minus ul star v, this is mx plus ny, right? What we want to do now is we want to solve L of u is equal to f of xy, and we want to do this, so solve this with respect to the boundary conditions, number one of which is u is equal to some f of x on some gamma, which is a curve on the xy plane, and del u del n is equal to some g of x, again on the same gamma. Okay, so we want to do this, and what we're going to follow is something which is called the Riemann's method. Okay, okay, so what we have is that gamma, as I show you here, is this smooth curve, and x and y are the characteristic coordinates. The tangent to gamma is nowhere parallel to these I mean, these coordinate axes, okay? Now let P of zeta be a point where the solution to the Cauchy problem is sought, and we have drawn these characteristics PR and QR through P to meet the curve at Q and R, okay? We will assume that U, Ux, Uy are prescribed along this this curve gamma. Okay. Now let's say that, okay, let's call this particular region R. Let's call this region R, and let's say that del R is actually the closed contour. Uh, closed contour PQRP, which bounds gamma, okay, bounds R. Now we use Green's theorem, so we have integral over this R mx plus ny dx dy. By Green's theorem, this is the integral over this contour, and it's m dy minus n dx. This should be familiar to you. So what do you have? What we have is, so this particular thing, so what the right hand side essentially means, so let's actually turn this around. So del of R m dy minus m dy minus n dx is equal to double integral over R v L u minus u L star v dx dy, right? That is what we saw earlier. So let us split this integral up now, okay? So let's split this integral up. So this integral now becomes, this is what? It's integral over gamma m dy minus n dx plus integral over rp m dy minus n dx integral over pq m dy minus n dx. Okay. Now, now what do we have? Dy is equal to 0 on PQ and dx is equal to 0 on PR. So that means that what we get is integral of gamma m dy minus n dx. This is the whole thing, plus in the RP segment, the dx is equal to 0, so this is just m dy, and in the other segment, the dy is equal to 0, so this is n dx on PQ. This is again equal to this, having double integral over R of this guy, right? So this guy, so essentially this guy again, so it's just, yeah, the same thing. All right, very good. So let's again try to figure this out a little better. Okay, so now we have n dx, and remember what n was. So n is given by the expression here. So let's put these things back. So let's try and evaluate n dx now. So on PQ, you want to evaluate n dx. So this is integral of p to q b of u v dx plus integral of p to q v of ux dx. So what is this? So this becomes uv p to q, p and q actually, plus integral over pq u bv minus vx dx. Okay, so we have turned things around a little bit, and as you can see, that is what is going to happen. So we have integrated by parts, and yeah, so that's the solution. So now, so what we have is the following. So uv p is equal to uv at q minus integral pq of u bv minus vx. Similarly, there is going to be an integral over rp u a v minus vy. So this one has a dx and this one has a dy, of course, minus the integral over the gamma m dy minus n dx plus this double integral over r vlu minus ul star v dx dy. So we have just used this and a similar thing for the other integrals. So we have used it for this one and this one, and we have rewritten the equality that we have here as this guy. Okay, now let's choose v v x y xi eta as solution to the adjoint equation L star v is equal to 0. Okay, and so this is choose, and this satisfying boundary conditions. One would be Vx is equal to Bv when y equal to eta, so that is on PQ. Number two, Vy equal to Av when x equal to xi, so that is essentially on PR. And thirdly, V is equal to 1 when x equal to xi, y equal to eta. Okay, so we choose this. So we are going to call this function, this particular function, we are going to call this a Riemann function. Okay, so then what do we get? We get u at p is equal to uv q minus integral gamma u AV minus VY dy minus B VBU plus UX dx plus double integral of on R of V of F dx dy. So this happens because you'd remember that L of U is equal to F, right? L of U is equal to F, the other function vanishes, and that's what you get. All right, so this is going to be called the Riemann-Green solution to the Cauchy problem when U, Ux are prescribed on gamma. So this is the Riemann-Green solution to the Cauchy problem when U, Ux are prescribed on gamma. So we can do a quick, so this is what I wanted to actually show you briefly here. And I am going to leave you guys with 3 exercises. And if there is trouble, we can again go through it. I'll give you some material for this one as well. So I'll say that, okay, obtain the Riemann solution for the equation del 2u del x del y equal to fxy given 1 u is equal to f of x, small f of x on gamma, and 2 del u del n is equal to g of x on gamma, where gamma is the curve y equal to x. Okay, so that is going to be one thing that you guys should work out. I'm going to give you another couple of problems. Verify that the Riemann-Green's function for del 2u del x del y plus twice 2 over x plus y del u del x plus del u del y is equal to 0, subject to u equal to 0 del u del x equal to 3x squared on y equal to x is given by vxy xi eta equal to x plus y twice xy plus xi minus eta x minus y plus twice xi eta divided by xi plus eta cube, and obtain the solution in the form u is equal to x minus y twice x squared plus or minus xy plus twice y squared. Yeah, so as I was saying, this is a short lecture, and what I will be doing is I'll also be forwarding you some material on this, so that hopefully this is a little clearer. So that's it for now, and we shall be moving on to Green's functions for PDEs in the next 3 lectures. Okay, so that's next 2 or 3 lectures. We'll see how we can go about doing that. But yeah, so that's that for now, and I'm going to see you guys very soon. Thank you.